All right, in this activity, we're going to explore probability. So for exercise 1, we're going to assume that you're at a carnival and decide to play a game where a person is flipping a coin. When you get to the table, you find out that all you have to do is guess which side of the coin will be facing up after it is tossed. You are assured that the coin is fair, which means that each of the two sides, heads and tails, has an equally likely chance of occurring. So first it asks us, what is the sample space? Remember, those are all the different possibilities or possible outcomes. So we're thinking about flipping a coin, the options are either heads or tails. So we're going to write it in our set notation. I'm going to just write H for heads and T for tails. What do you think the probability of the coin landing on heads would be? So it seems like 50-50 chance is sometimes what we'll say. So we're going to say 50%. You could also think about it that we know maybe that heads is only one of the options out of two, which is the same thing as that 50%. So now I'm going to flip a coin 30 times and list the results of each trial. So this would be different for you, but you should really stop and flip your coin 30 times. So I'm going to put my results in the table, but again, yours could be different. And it will be different. The chance or probability of us getting the same is highly unlikely. Some might even say the probability would be like 0. All right, so these are the results that I have. Again, you need to be calculating this for whatever your rolls are. And so again, doing it 30 times. If I add up all of my heads that I have here, it actually is a total of 13, and my total tails is 17. Remember, these two numbers together should add to our total number of times, which is 30. So for that probability, we're going to write for the probability of heads, we got 13 out of 30 flips. Okay, so that's the experimental probability. Our tails would be 17 out of 30. And so we were saying about 50%. So when we actually did the experiment, it looks like we're getting heads 43% of the time, and our tails was 57%. And you can see those two numbers add to 100. So then it asks if there's anything interesting that occurred in the data set. So, I mean, your data set might be different than mine. Yours might have more heads than it had tails. One thing that I thought was interesting is how many tails I got in a row there. That's a lot. Sometimes there's an assumption made that like you're going to get a few tails, then you should get a few heads to kind of even that out, get that 50-50. But when you do the experiment, it doesn't always turn out like that. Now we're going to put together a bunch of data because doing 30 flips is a good experiment. But if we combine the 30 flips from the entire class, something interesting should be happening. So I found an app that would let us kind of put together what it would be like if we had 1,000 coin flips. So kind of mimicking about 30-something people flipping the coins 30 times. So you want to click on the link that I'll send on the announcement on Tuesday, and that link will take you to something called StatCrunch, where you can see what happens when you do 1,000 flips. And actually with that, there's a nice graph that shows what happens the more that you flip. And for mine, again, yours will be different. I got 503 heads, which means I have 497 tails. And so that is out of that 1,000 coin flip, which gives me about 50.3% being heads and 49.7% being tails. And notice that these numbers are a lot closer than what we had previously when we were just doing the 30 coin tosses. So as we do more and more larger experiments, what happens, and this actually has a fancy name, it's called the law of large numbers, we're going to get our experimental probability to approach the theoretical. It approaches or gets closer to the theoretical probability, which is why those numbers are really close to 50%. And so if I think about what's going to happen on the next toss, it's really a 50% chance of getting each of those with the next toss. So you can't really say what's going to happen. Even if you got like a whole bunch of heads in a row, you can't necessarily tell that the next one would be tails. So when you look at this next question, and assume you could win $1 million if you could guess what the results of the next toss will be, what would you bet on? Really, it's a 50-50 chance. Again, even if it was like heads, 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 like you had so many heads in a row, each one has a 50% chance of happening, head or tails, so you can't really guess what's going to happen next. All right, for exercise number 2, we're still at this carnival, and we're going to play a different game. This time, the person is rolling a die. When you get to the table, you find out all you have to do is guess which side of the dice will be facing up after it's rolled. Here, sure, the dice is fair, which means that each of the 6 sides has an equally likely chance of occurring. So our sample space for this is going to be all the sides. There's 6 of them, so there's 1 on one side, 2, 3, 4, 5, all the way to 6. Those are all the different possibilities. So what do you think the probability of landing on a 5 would be? Well, there are 6 numbers to choose from, so our total sample space has 6 elements in it, and the number 5 is one of those. So it looks like it should be 1 out of 6, which if I want to write that as a decimal, it's going to be about 16.7% chance. Now we're going to roll the dice 6 times to see what's going to happen here. And when I roll my dice, I'm going to get a 4, 3, 2, 1, 1, and 4. Based on those 6 rolls, it wants our experimental probability. So we know that, let's look at rolling each outcome. So roll 1, that happened twice, so I'm going to have 2 out of 6, which is equal to 1/3. To roll a 2, that happened 1 out of 6 times. To roll the 3, that happened 1 out of 6. To roll 4, that happened 2 out of 6, which is 1/3. And to roll 5, that never happened, so that's 0 out of 6, so really 0. And rolling the 6 also happened 0 out of 6, which is equal to 0. And so we said for rolling a 5, theoretically, it should be 1 out of 6. And you can see that after 6 rolls, it's like kind of random. So let's see what happens if we do it more. Again, your results will be different because you rolled your own die 6 times, and it is not likely that we would have the same rolls. So when we roll the die 24 times, let's see, I ended up that I rolled a 1 twice. I rolled a 2 5 times. This I had tallied it before I wrote it in here. I rolled a 3 3 times. I rolled a 4 4 times. I rolled a 5 4 times. And I rolled a 6 6 times. So those are my 24 rolls. I could put in my original 6 rolls, so if I want to add those to just have more data in here, 4 3 2, 4 3 2 1 1 4. Again, yours will be different, but I added in this last row so that way I could have 30 results again, because it seems like the more results that you have, then you're going to get closer to that experimental probability. So let's look at the probability now. So rolling a 1, it looks like that happened 1 2 3 4 times. So 4 out of the 30. Rolling 2 happened 1 2 3 4 5 6 times. Rolling a 3 happened 1 2 3 4 times. Rolling a 4 happened 1 2 3 4 5 times. Rolling 5 happened 1 2 3 4 times. Rolling 6 happened 1 2 3 4 5 6 times. And if I look at my totals, let's see, so I have 4 8 12 18 23 29. I missed the 4, so let's replace that 4. That was actually 6 out of 30. And so we can reduce the fractions, or we can write the percents, however you want to do that. I'm going to stick the percents in here. So throwing in those percents, you can see I was like 13 to 20%. And if you look back up, which I'm going to go to our previous page here, we said the probability of rolling an individual number like 5 was about 16.7%. And so you can see that when we just rolled 6 times, we got a lot of 0% going on. We got a couple 1/6, then we got 1/3, which is pretty high. But then the more that we rolled, we were able to get closer to that 16%, 13 to 20. So, I mean, it's kind of interesting that we didn't get, of course, like right on that 16.6 or 0.7%. So that's kind of interesting. I did have a lot of 6s when I did my next 24 rolls. So I thought that was kind of interesting because in my initial 6, I didn't have any 6s and I didn't have any 5s. So what was interesting about your data? Check that out. And for this last part, comparing that experimental and theoretical probability of rolling a 5, well, the theoretical that we said was 1 out of 6, which is about that 16.7%. And then experimentally, when we look back at rolling a 5, we're close to it. We got about 13.3%. And that was much closer compared to when we did our initial 6, and we got the probability of rolling a 5 to be 0. So what we're noticing is that the more times that you perform an experiment, you're going to get closer and closer to its theoretical probability, which is that law of large numbers.